Hello and welcome to a slightly different video here for today. So for today's video here, I'm going to think about this in two parts. So for the first part of the video here, shouldn't take more than a few minutes really. I'm just going to quickly discuss paper 1, that you should have sat a few days ago, and what to expect for paper 2 here. So you can already kind of see it on the screen, right? I've got a list of the different topics here that I would be expecting for paper 2, okay? And then for the second part of the video, right, which will be the majority of the video, we're going to work through some practice questions here based on these topics, right? So as you can see then, small angle approximations, indices, quadratics, so on and so on. But we'll discuss this in a little bit more detail shortly. So as we said then, paper 1 was a few days ago. And generally speaking, the feedback here from paper 1 is pretty positive. I think the only real kind of complaint here for paper 1 was the timing, given that there was 16 questions compared to the normal 15. But generally speaking, from what I saw of the paper, it looked pretty good. And hopefully, many of you find that to be the case. Now, another question that keeps popping up here is about grade boundaries. And what I would say here in terms of the grade boundaries is at this point, I wouldn't even consider it, right? It's not worth stressing about because there's still 200 marks to play for. So you've got paper 2 coming up next week. And you've also got paper 3, which is the applied paper, right? 50 parts being, or 50 marks being stats, and 50 marks being mechanics. So, like I said, right, at this point here, I would not be kind of stressing or being worried about the grade boundaries, okay? So, just focus on for now, paper 2 and paper 3. Now, the thing here is with paper 1, we know what topics came up, right? So we know what topics came up for paper 1. And generally speaking here, Edexcel do not mix the topics from paper 1 with paper 2, right? Obviously, there is a set list here of things that they need to assess. So we kind of have a good idea then of what to expect here for paper 2. And I've compiled this list here to give you an idea as well. So let's just quickly run through this list here. So I appreciate that this list is quite lengthy and they're probably not going to be able to ask absolutely everything on this list here, but this is what I would be focusing on, okay, in terms of my revision, right? And to kind of nail down that revision, this is the list of topics that I would be focusing on. So starting off then we have the small angle approximations. Now, the small angle approximations is normally kind of thrown in, you know, the first few questions, question 1, question 2, question 3, something like that. However, it can also appear towards the end of the paper mixed in with something like trigonometry or differentiation. So keep an eye out for that. It can be embedded within a different question. Now, indices hasn't made an appearance really, but this is something that might not come up, but generally speaking, indices should be pretty straightforward. I wouldn't spend a lot of time on this, but just make sure that you're sharp with the different rules of indices here. Quadratics, this could be potentially quadratic modeling. So just make sure then that you're confident with quadratic modeling. We do also have a video on quadratic modeling, so if you want a little bit of extra practice, go and check that out. So for paper 1 then, we saw arithmetic sequences. So clearly, arithmetic sequences are not going to pop up again. So I would expect geometric sequences to occur. Again, this could be in the context of modeling. So just make sure then that you're familiar with how to answer questions based on geometric sequences in a modeling context. Now, sticking with sequences and series here, we also have recurrence relations and sigma notation. So again, this hasn't occurred on paper 1. So there's a very good chance that you would expect one of these, either recurrence relations or sigma notation. They can pop up within the same question, but I would expect something either on recurrence relations or sigma notation. Now, the Trapezium Rule, again, hasn't popped up, so very likely that we'd expect something on the Trapezium Rule. We haven't seen much in terms of differentiation here, so the Newton-Raphson method I would expect, alongside differentiation from first principles, so make sure then that you know how to differentiate sin x and cos x from first principles. Of course, it might not be sin x and cos x from first principles, but 5 marks, really easy 5 marks, right? Just make sure that you know how to do that. We also have implicit differentiation, parametric differentiation as well. Obviously, connected rates of change could occur. So just make sure then that you're confident with differentiation, right? It's going to make up quite a large part of paper 2. So just going back here, we haven't seen anything for the binomial expansion, and there will definitely be a question on the binomial expansion. So don't neglect that as part of your revision. Like I said, there will be definitely something on the binomial expansion. Logs and exponentials. So again, this could be in the context of modeling here. So exponential modeling. There's also linear models, and going to nonlinear models and vice versa. You could get a question on that. Partial fractions. So partial fractions is a bit of an interesting one because, as you can see here, this can be mixed with a few different topics, right? So you might get a question here on the binomial expansion that requires partial fractions. Same again here with integration and also differential equations. So there's a very good chance here that partial fractions is included in the context of one of these three topics here. I would expect differential equations or potentially binomial expansion as opposed to integration, but just make sure then that you're confident with each of these different topics here, mixed in with partial fractions. I've already mentioned differentiation here. In terms of integration, well, we've already seen integration by substitution, right? So I probably wouldn't expect that. Maybe a little bit on integration by parts here. I would definitely expect parametric integration, and I think I've missed it out here on the list, right? But there wasn't much on parametric, so I would expect parametric differentiation potentially. I would definitely expect parametric integration. I could be wrong there, but that's my prediction. So yeah, expect quite a bit on parametrics. We also have proof by contradiction. So we didn't see anything for proof by contradiction. And again, this is something similar to the binomial expansion that does come up pretty much every single year. Okay, so again, just make sure that you're confident with proof by contradiction. Functions and also the modulus functions. So for example, solving modulus equations, being able to sketch modulus functions, stuff like that. Generally speaking, I think that's pretty straightforward, but just make sure then that you're confident with how to do that. And then finally here, we have the harmonic identities and also these are the same thing, but some people know them as the R formulae. Some people know them as the harmonic identities. It's the same thing, right? But just make sure then that you're confident with whatever you call it, okay? Now, again, that could also be in the context of modeling here. So usually questions to do with either the depth of water in a harbor, for example, or temperatures in a room or a warehouse, or I don't know, a tank of water, something like that, right? It's never particularly interesting, but you get the idea. Be aware of this list here. These are the topics that you should be revising now for paper 2. I wouldn't really spend any time revising topics that have already occurred. I can't speak anymore. Have already occurred on paper 1. It's probably not, a particularly good use of your time. We're also going to cover here some A-level maths questions based on these topics here that haven't occurred. So I think I've pulled out about 10 questions here. Feel free to use this as a predicted paper as well. We have already released paper 1 and paper 2. I'll put a picture here somewhere on the screen right now, or I should do if my editing skills are up to scratch. And like I said, go and check those out if you are looking for even more A-level maths revision in the run-up to your upcoming exam. But yeah, feel free to use this as a predicted paper. Now, it's not going to be perfect. I'm not going to put in 16 questions. I might include a few extra that I haven't covered in the video. And you'll be able to download this on our website, AJMaths.co.uk. We've also got worksheets. 8 predicted papers in total now. We will be releasing the mechanics one as well very, very shortly. But yeah, hopefully this video here will help you now in your final days of preparation here for paper 2. Okay. So before we get started then with paper 1, question 1, all I wanted to say here was best of luck with paper 2. Like I said, the feedback for paper 1 was pretty positive. I think most people did find it to be quite a good paper. I would expect paper 2 to be a little bit more challenging, personally, but, not to scare you, right? But yeah, I would expect it to be a little bit more challenging. So let's not waste any more time then, and let's just get started here with question 1. So let's just make a start here then with question 1. And as we can see then, question 1 here is on indices, right? So should be pretty straightforward just to get us started here. So for part A then, what do we need to do here? So we're given that y is equal to 3 to the x, and we want to express each of the following here in terms of y. We need to write each expression then in its simplest form. So this question here is just basically an application of the laws of indices, right? Should be pretty straightforward for the most part. So to get us started here, we have 3 to the power then of 3x. So using the laws of indices here, we can write this as 3 to the power of x all cubed. And we know then that 3 to the x here is simply y. And in that case then, we just get y cubed. Nice and straightforward there. Now for part B then, so what I've got here is 1 all over 3 to the power then of x minus 2. So again, all I want to do here is just use the laws of indices. I'm going to rewrite my denominator here. So this here then is just the same as 1 all over 3 to the x times by 3 to the minus 2. Okay? And I can split this up here then. So this is the same as 1 over 3 to the x times 1 over 3 to the minus 2. So 1 over 3 to the x then, that is just the same as 1 over y, because 3 to the x is y here. I've got 1 over y times by them. So 3 to the minus 2 then, that is 1 over 3 squared. So I've got 1 over 9, which is just the same here as 9. So 1 over y times by 9 here, and that just simply gives us 9 over y there. Okay, that is the solution to part B. And then finally here to finish with, we have part C. So for part C then, we have the following. So definitely the trickiest part here of this question, right? So I've got 81 all over 9 to the power then of 2 minus 3x. Right, so where do we begin here? So my numerator here is 81, which is just 9 squared. So I've got 9 squared, and that's all over 9, or then of 2 minus 3x. Okay? So because the base here is the same, right? 9 and 9 here, we can just write this as 9 to the power then of 2 minus this here, this power. So 2 minus 3x, like so. So 2 minus 2, they just cancel here. Minus of a minus becomes positive. So we get 9 to the power of 3x. Well, 9 then is just the same here as 3 squared, right? So I've got 3 squared to the power then of 3x here, like so. Multiplying out the powers here then, I get 3 to the power then of 6x. Okay, and similar to what we did here then with part A, I can write this here then as 3 to the x all to the power of 6. And again, we know that 3 to the power of x here is simply y. So what I've got here then is y to the power of 6 there. And there we have it then. So that gives the solution here to part C and the solution to question 1. So moving on to question 2 then, where we now have the trapezium rule. So generally speaking, the trapezium rule here is what I call a gimme, in the sense that really the marks here are 3 marks. I don't mean 3 numerically, I mean 3 in the sense that the questions are, generally speaking, nice and easy. So let's just get started then with part A here. So for part A here, well, for this question I've got figure 1, right? Figure 1 then shows a sketch of part of the graph of this equation here. I've got this table below, which gives values of y rounded to 3 decimal places. Okay. And for the first part of the question then, as we would expect here, what we want to do then is use the trapezium rule with all the values of y from the table to find an approximate value for this integral here. So we've got this integral here from 2 to 11. I'm integrating then 12 all over the square root of x squared minus 2. I'm integrating here then with respect to x. Now, like I said, these questions here are pretty straightforward, right? It's just an application of the trapezium rule. And we don't even need to worry about the table here and getting the correct values for y. The full table is already given to us. So to begin with here, let's just find h then. So h here, we can easily observe by using the table. So 5 minus 2 is 3, 8 minus 5 is 3, so h is 3 here, okay? So what do we get here then? So this integral here, using the trapezium rule, will be approximately, and we should have just about enough room here. We get h over 2, so I get 3 over 2 there. So 3 over 2 times by, so what I do here is the first y value plus the last y value, and then 2 lots of all the other y values, right? If you can remember that, the trapezium rule is really straightforward. So I get 8.485. So 8.485 plus 1.100, just 1.1. 1.1 plus 2 lots of everything else, right? So 2.502 and also 1.524. Bosh. Okay. So nothing extravagant here. Just put this into your calculator, right? And if you do this correctly here, then what you should get, does it ask for it to 2 decimal places, right? So I get 26. I get 26.4555. Yeah, 3 5s there, like so. So I'm writing this to 2 decimal places here as part A. As for what I get here then is approximately 26.46 there. Okay. As we just said then, that's to 2 decimal places here. Like I said, pretty straightforward. It's just an application of the Trapezium Rule. Now for part B then, a little bit more complex here, but again, should be pretty straightforward. And these types of questions are really, really common. So make sure then that you know how to answer something like part B here. So let's just run through how we would answer something like this. Now, if you really, really want to, you can form the table here for X and Y again. That is really, really unnecessary. Okay. We can easily do this then by just observing the integrand here. So what I've got then is the integral here from 2 to 11 of 1 plus 6 all over the square root then of x squared minus 2. Okay, and again, integrating here with respect to x. Now, just notice then, my limits here don't change from 2 to 11, so that's fine. We don't need to worry about that. Now, what I've got here is this 1 included with my integrand. So what I can do here is use linearity and split this integrand up, right? We can split this up into 2 separate integrals. I've got the integral here of 1 with respect to x from 2 to 11. And also then the integral here of, so again, from 2 to 11 of 6 all over the square root then of x squared minus 2. Okay, again, with respect to x. Now, this integral here, the integral of 1 with respect to x from 2 to 11, nobody should be having issues with this. If you are, you're probably cooked. But what you should get then is just x here from 2 to 11. We get 11 minus 2 that's just 9, right? When I evaluate this definite integral here. Now, this one here, what do we do with this? Well, just notice then, this here is very, very similar to what we had in part A, right? In fact, it's just a half of what we had in part A. So all I do then is I take my answer from part A, as part B suggests, right? Use your answer to part A. So I take this answer here then from part A. We want half of that because this integrand here is a half of this integrand here. I get 9 plus a half times by 26.46. Again, just put this into your calculator, right? We don't need anything fancy here. And if you do this correctly, then what you should get here is 22.23 there. And there we have it then. So 22.23 is the solution to part B, and 26.46 is a solution to part A there. Okay? And there we have it then. So that gives the solution here to question 2. So moving on to question 3 here, as we can see then, we now have a question on the binomial expansion. Now, if you are like me and don't personally enjoy the binomial expansion, just take your time with these questions. I am prone to make mistakes as I answer these questions. So I will be very, very careful as I answer the question here for YouTube. But yeah, just take your time, right, if you get this on an exam. Generally speaking, the marks are pretty straightforward to obtain. More than anything, you're more likely to make a very tiny mistake. Okay, so let's just start then with part A here. So what we've got here then is f of x. So f of x is equal to 125 minus 5x all to the power of 2 over 3. So for the first part of this question, part A, what we want to do here then is find the binomial expansion of f of x in ascending powers of x up to and including the term in x squared. So to begin with here, let me actually just start by writing down f of x here, right? It's always easiest to do. So f of x is equal to, so it's 125 minus 5x all to the power then of 2 over 3. Okay. Now, the first thing to notice here is we need 1 here, right? I need 1 minus some multiple of x. The issue here then is we don't have 1. I've got 125. So what I do here then is I factor out this number, right? And once we do that, we obtain 1 here. So I get 125. We need to factor out the 125 here. 125, like so. Now, once I factor this out here, we still need to apply this power. So I get 125 to the power then of 2 over 3 times by, we now get 1 here inside the bracket, and factor out then 125 from the minus 5x here, I get minus 1 over 25x there. Okay, sorry, let me just reword that. Let's just be slightly careful here. So mistake number 1, minus 1 over 25x there, right? The x doesn't go as part of the denominator here. So 1 over 25 is my coefficient here, or minus 1 over 25. And this here then is all to the power of 2 over 3. Okay. Now at this point here then, we can now apply the binomial expansion, right, to this part here. So 125 to the power 2 over 3. So I get 5 squared is 25. So I've got 25. So 25 times by them. And inside this bracket here then would be the series expansion here of this. So let's just go here nice and slow, right, so I don't make a mistake. So to begin with, we get 1. Nice and straightforward, right? I probably should have included the formula here on the screen. Obviously, just grab your formula book. The result that you need is given in your formula book. So we get 1. Nice and straightforward. I then get my power here. So that's 2 over 3. So 2 over 3. And I times this here then by minus 1 over 25x here. Like so. Perfect. Moving on then, what do we get here? So I get 2 over 3. So 2 over 3. I then times this by 2 over 3 minus 1. So 2 over 3 minus 1, that's just the same as 2 over 3 minus 3 over 3. So I get minus 1 over 3 there. Like so. This here then is over 2 factorial. And then I times this here by, it's minus 1 over 25x. Like so. And we now square this term here. Like so. Okay, now this would just keep going on and on, but obviously we're only concerned here about going up to the term in x squared, right? So let's not do any unnecessary work here, and we'll just terminate this process for now. Okay. So at this point here, it's just simply a matter of using your calculator, right? Obviously, don't start trying to do this by hand. Just use the calculator, because generally speaking, your calculator should also give you the coefficient here in its simplest form, right? Because we want the coefficient of x and x squared here as simplified fractions. So obviously 25 times 1 is 25. Again, just put all of this into your calculator, right? So for the x term here, given the coefficient of x here in its simplest form, I get minus 2 over 3x. So minus 2 over 3x there. And then for the x squared term here, again, given the coefficient of x squared in its simplest form here, what I get then is minus 1 over 225 x squared there. Okay, and again, this would just keep going on and on, but we're only concerned about going up to the term in x squared. So there we have it then, nice and straightforward. That gives us the solution to part A. Now for part B then, again, pretty standard stuff here, just a quick follow on from part A. So it says, use your expansion to find an approximate value for 120 to the power of 2 over 3, state the value of x for, or which you have used, and also show your working, and give your answer to 5 decimal places. So what I want here then is 120 to the power of 2 over 3. So starting off then, f of x here is 125 minus 5x to the power of 2 over 3. So notice then, these are pretty similar. That's obviously the whole point of the binomial expansion here in this context. So I've got 125 minus 5x all to the power of 2. So all to the power of 2 over 3. And what I want then here is for the inside of my bracket here to to be equal to 120, right? I want to equate those. So I think most of you kind of looking at this would be able to see this quite intuitively, but just in case you are struggling then, I've got 125 minus 5x is equal to 120. Subtract 120 off both sides and add 5x to both sides here. And in that case then, what I get here is 5x is equal to 5. And therefore then, solving for x here, we obtain x equals 1. Okay, so the value that we're going to substitute in here for x is simply 1. So nice and straightforward then, we just simply use this expansion here with this value of x here that we've identified. And in that case then, 120 to the power of 2 over 3 is approximately, I get 25 minus 2 over 3 times by 1. So just simply minus 2 over 3. And then finally, I get minus 1 over 225 times by 1 squared. So again, we simply get the coefficient here. So minus 1 over 225. So minus 1 over 225 here. And of course, just use your calculator here, right? So if you do this correctly here, what you should get then for the approximate value of 120 to the power of 2 over 3 is, and again, this is to 5 decimal places as the question asks for. So I get 24. So 24.3289 there. Okay. And there we have it. As a quick sense check, if you get a question like that right, quickly just put into your calculator then 120. And I'll just do it here. So 120 to the power of 2 over 3. And you should get something pretty close to this. Okay. So once I put 120 to the power of 2 over 3 into my calculator here, what I get then is 24.32880798. And it's pretty close to this. Obviously, if I get something completely different, so for example, then if I put 120 to the power of 2 over 3 into my calculator, and for example, then I get 30, I know something's gone horribly wrong, okay? Your answer, your approximation here should be pretty close, okay? So just use that as a quick sense check in an exam, okay? So there we have it then. That gives us the solution here to question 3. All right, so moving on to question 4 here. As we can see then, we now have a question on logarithms here. So for the first part of question 4 then, it says using the laws of logarithms, we want to solve the following log equation here. The second part as well, obviously, we'll cross this bridge when we get to it, but it looks a little bit funky, right? And I quite like this part of the question. It does involve a little bit on sigma notation as well. Like I said, we'll take a look at this very, very shortly. So starting off then with the first part here of question 4. I don't know where part A has gone, so I'm going to call it part A, part 1. In fact, I don't even need part A. Let's call it part 1 here. Okay. So what I've got here then is this equation. So I've got log 4x base 3 plus 2 is equal to log 5x plus 7, again, base 3 here. So because my two logarithms here have the same base, right, what I can do then is combine these into a single logarithm. So let's subtract then log 4x base 3 off both sides here. So I get log of 5x plus 7 base 3 minus log of 4x, again base 3, that doesn't change, is equal to 2. Okay. Now on the left hand side here, we have a difference of logarithms here where they have the same base. So what I can do here then, as we've just mentioned, right, is write this as a single logarithm. So what I get here then is I get 5x plus 7. And as well, don't forget here, this should be log. So don't forget the log, right? If we're writing this as a single logarithm, it's always a good step. I get 5x plus 7 all over 4x. And this here then is equal to 2. Okay. Now we're looking to solve for x here, right? So what I need to do then is get rid of the logarithm here on the left-hand side. So we're going to anti-log here. So nice and straightforward then. What I get here on the left-hand side, once we anti-log, so I'm just going to cancel out the log here. I get 5x plus 7 over 4x. So 5x plus 7 all over 4x here. and that is equal to 3 squared. So 3 squared is 9, right? Like so. And again, all we're looking to do here is just solve for x. So I'm going to times both sides then by 4x here. So on this side, I get 9 times 4x, which is 36x. I've got 36x is equal to 5x plus 7. Subtract 5x off both sides then. I get 31x is equal to 7. And then finally here, x is equal to 7 over 31, right? Hopefully nothing too challenging there for the first part of this question here. Now for the second part of this question here, like we said then, it looks a little bit funky here, right? I've got sigma notation, as we can see here, and we also have logs. So I'm given this here, and I want to find y in terms of a, giving your answer in its simplest form. Right, so where do I begin here? Well, to begin with here, let's just start with the left-hand side then. So I've got the summation. I've got the summation here of log of y to the r, of y to the r here, base a, from r equals 1 to 2. Okay? Now, in terms of this series here, right, we're only going to have 2 terms. That's when r equals 1 and also when r equals 2. So when r equals 1 here, I get log y. So it's log y to the 1, but that's just log y base a. So I get log y base a. And then when r equals 2 here, it's just the same, but now the power here is 2. Why? So it's 2, right? I can't speak. So it's log y squared base a. So let's just write that down as well. So log y squared base a again. Okay? Hopefully, that seems quite intuitive. Now, what about with the right-hand side here? What can we do with that? Well, again, let's just consider here what happens then when r equals 1 and r equals 2. We've got the summation then from r equals 1 to 2 of, so I've got log y base a all to the power of r here. So when r equals 1 here, we just get this term again, right? Because that's log y base a to the power of 1. So log y base a, nice and easy. And then for my second term here, this when r equals 2, what I get then here is log y. So log y base a all squared. Okay. Now, this summation here, which is just these 2 terms, is equal to this summation here, which is just these 2 terms here. So let's just equate then these 2 expressions here. Okay. And we'll see what happens. So in that case, then what I get here is log y base a plus log y squared base a is equal to, so we're going to get log y base a, so log y base a plus this term here, so log y base a all squared. Okay. Now straight away then, I can see that these 2 terms here just cancel, right? So what I've got here then is, so I've got log y squared base a here is equal to, so it's log y base a all squared. So what I can do here then is use the laws of logarithms, and what I'm also going to do here is make one side of this equation equal to 0, right? So I can bring this 2 down here in front. So I get 2 log y base a. And now let's just subtract this here then off both sides, right? I get minus then log y base a all squared. Oops, all squared. Okay. And this here then is equal to 0. Now at this point here, what I think is probably easiest then is if I change this here, so this log y base a all squared, if I just write that as an actual product then. So what I've got here is 2 log y so 2 log y base a, minus them, so I've got log y base a, times by itself again, right? That's all this squared here is telling us. So we're going to have also got log y base a, and this here then is equal to 0, okay? Now, at this point here, we want to find y in terms of a. So all I'm looking to do here is solve for a. Solve for y, sorry. Okay, so what I'm going to do then is factor out here log y base a, right? I've got a log y base a here, or 2 lots of that anyway, and also this product here of log y base a. So let's factor out then the log y base a here. So we factor out log y base a times by them. So inside the bracket here, I need to get 2 because log y base a times 2 gives us 2 log y base a. And then this part here, right, I'm just going to get simply minus log y base a. And all of this here then is equal to 0. And if I'm solving for y here, right, what I'm going to do then is take this here as my solution. So in that case then, I've got 2 minus log y base a is equal to 0. So 2 minus log y base a is equal to 0. In that case then, I get log y base a is equal to 2. And don't forget then, we're solving for y here. So nice and straightforward then. I'm going to get here for y. Obviously, I need to anti-log here. We just want y then. So therefore, y is equal to a squared. So y is equal to a squared. And there we have it. Beautiful. Okay. Now, part A was pretty straightforward. Part B, though, like I said, a little bit more involved here, a little bit more complicated. But hopefully, this is quite a nice challenge there for logarithms, right? It's not particularly straightforward and does involve a little bit here on sigma notation. Nothing crazy, but, does involve another topic there as well. Okay. So there we have it then. That gives us the solution here to question 4. All right, so moving on to question 5 here. As we can see then, we now have a question on implicit differentiation. And at some point within paper 2 here, I would expect a question on implicit differentiation. So hopefully this question here will give you a bit of a guide as to what to expect then maybe for paper 2. So what have we got here then for this question? So I've got the point P with these coordinates here, and the point P then lies on the curve with this equation here. And all we want to do then is find an equation of the normal to the curve at the point P. Okay? So to get us started here, all I'm going to do then is differentiate this equation here implicitly, right? Because I know then, if we want the equation of the normal to the curve at the point P, then I will need dy by dx here. Okay, we need the gradient. And subsequently, if we want the equation of the normal, we do need the normal gradient. But we'll cross that bridge when we get to it. So let's just start then by differentiating implicitly here, right? Now, on the left-hand side then, I've got a product of functions here. So clearly, we do need to use the product rule. So u here would be 4x. And v then is the remaining function here of sine x. We also need then u prime and v prime here. Again, this should be nice and straightforward, right? U prime is simply 4, and v prime here is cos x. Okay? And in that case then, if I'm differentiating this here, by using the product rule then, we simply get 4x cos x plus 4 sine x. Okay? So, let's just make a note here then. So I get 4x cos x, like so, and I also get plus 4 sine x. Okay, so that's the left-hand side there dealt with. Now, on the right-hand side here, well, I've got multiple terms, but just differentiate as you would anyway, right? We just go term by term here. Now, for the pi y squared here, just be slightly careful, okay, because we are now involving y here. So, to differentiate this here, treat it as if it was just x, right? So if this was pi x squared here, we would get 2 pi x. But because it's now y squared here, to finish with, we just need to times through by dy by dx here, right? That's the whole point of implicit differentiation. So I get 2 pi y So 2 pi y times by dy by dx. Like so. And then the plus 2x here, nobody should have any issues differentiating that. That's just simply plus 2, right? Good stuff. So what I want here then is dy by dx, right? So I'm going to start by just subtracting 2 off both sides. So 2 pi y dy by dx is equal to, so this is just my single dy by dx here. Sometimes with implicit differentiation, you would get 2 dy by dx's. And obviously in that case, you need to group them together and factorize. But in this case here, it's just a single dy by dx, right? So pretty straightforward. To get 4x cos x plus 4 sin x minus 2. And then finally here, dy by dx then is, so it's just this here divided by 2 pi y, right? So 4x cos x plus 4 sin x minus 2 all over 2 pi y. Okay, now clearly I could divide through by 2 here. So I'll just quickly do that then. Just make it look a little bit neater here. Obviously you don't have to, but that would become 2x, that would become 2, and that becomes minus 1, and that just cancels. So we just said then we get 2x plus 2 sin x minus 1 all over pi y. Okay, and there we have it then. So that is dy by dx there. Now, what I'm going to do then is find the value of the gradient here. So dy by dx then at this point here, p, right, with these coordinates here. So when x is equal to pi over 2 and y is 1, what do we get here then for dy by dx? So in that case then, dy by dx here is equal to get 2 lots of pi over 2, that's just simply pi there. So pi cos pi over 2, like so, plus 2, so plus 2 sine pi over 2, like so, minus 1, and this here then is all over pi y. So pi times by 1, so it's all over pi there. Okay. So what do I get here then? So I get, so I'm going to get 1 over pi here. So just put this into your calculator, right? So pi times cos pi over 2 plus 2 sine pi over 2 minus 1 all over pi. I simply get, as we just said then, 1 over pi. So 1 over pi there. Okay. Now, just be slightly careful here, right? Because we want the equation of the normal. So this here is not my gradient. I want to use the normal gradient here. So in that case then, my perp gradient here, so perp m is equal to, so flip this here, times through by minus 1. So I get pi, times it by minus 1, and we get minus pi there. Good stuff. Okay. And then to finish with here, I'm just going to use then the equation of a straight line here, right? So y minus y1 is equal to m times x minus x1. So x1 here, just make a note then. So x1 is pi over 2 and y1 is 1, right? It's just this point here. So let's just put all of this here then together. And what I get then is y minus y1, which is 1. So y minus 1 is equal to m, which is minus pi here. So minus pi times by x minus x1, which is pi over 2. Like so there. Okay. And at this point here, I would just recommend leaving your answer in this form here, right? There's no need to kind of, try and simplify this or anything like that. It doesn't ask for the equation of the normal in a specific form. So I would just recommend then leaving your answer as this here. Okay, there's no need to try and simplify this. Just leave it as it is. Okay, so there we have it. So therefore, what I'll do is I'll just write it out again here and just state that that is the equation of the normal. So therefore, y minus 1 is equal to minus pi times x minus pi over 2. Like so, is the equation, or is an equation, I should say, is an equation of the normal to the curve at P. Okay, and there we have it then. Good stuff, right? So hopefully nothing too challenging there. So that gives the solution here to question 5. Now for the next question here, question 6, as we can see then, we're now dealing with the harmonic identities here. So sometimes called the R formulae, they are just the same thing, but whatever you prefer to call it. So let's just make a start then with part A here. So for part A then, what do we want to do here? So we want to express 3 cos theta plus 4 sine theta in this form here. We've got 3 cos theta plus 4 sine theta is identical to r cos, so r cos of theta minus alpha. Okay, so r and alpha are constants, r is strictly greater than 0, and alpha is between 0 and 90 degrees here. All right, so where do we begin here? Well, there's 2 ways to really go about this here, right? Some people like to kind of use the compound angle formula here. So for cos of a minus b, where a is theta, b is alpha. So you list that out and then compare coefficients and then go from there to obtain alpha and r. You can do that. However, I do think that is a little bit unnecessary here, right? Because this is just a straightforward application here of the harmonic identities. So don't forget them. So r here is simply an application of Pythagoras. So r then is the square root of 3 squared plus 4 squared. Okay. This is one of our Pythagorean triples here. So we get the square root of 25, which is simply 5. So we obtain the value of r here, nice and straightforward. Now for alpha then, well, what I can see here is that tan alpha, so tan alpha here is equal to 4 over 3. So tan alpha is 4 over 3, and therefore in that case here, take tan inverse of both sides. So alpha is equal to tan inverse of 4 over 3. Now obviously just be very, very careful here, right? We're not working in radians for this question here. Often we will be working in radians, but for this question here, we are working in degrees, right? So obviously just be very, very careful for that. And if you do this correctly here, then what we get is 53 degrees there. Okay, so alpha is equal to 53 degrees there. Perfect. Okay. So to finish with then, let's actually just express it in this form here. So 3 cos theta plus 4 sine theta is identical to r cos of theta minus alpha. So r is 5. We get 5 cos of theta minus alpha, where alpha is 53. So minus 53 degrees there. Good stuff. So that gives us the solution there. Part A. Now for the next part of this question, then part B here, what do we want to do? So it says, hence find the maximum value of 3 cos theta plus 4 sine theta, and also the smallest positive value of theta for which this maximum occurs. So for part B then. Now the fact that it says hence find here would suggest that the answer from part A, that is this line of work in here, is probably going to be useful to help us answer part B. And that is the case, right? Because rather than working with this expression here as a sum of different trigonometric functions, it's just easier to work with a single trigonometric function here. And in this form here, I can easily see then that the maximum value of 3 cos theta plus 4 sine theta is simply 5. So let me just state here the max value. So the max value is 5. But why is that the case? Well, the reason that the maximum value here is 5 is because cosine has a maximum value of 1. So I've got 5 times by 1, which is simply 5, right? So the maximum value of this here is 5. And in that case then, the smallest positive value of theta for which this maximum occurs is, so at the max then, just make a note here, so at the max then, cosine of theta minus 53 degrees is equal to 1, right? Now we just want to solve for theta here. So if we just take cos inverse of both sides here, on the left-hand side, we just get left with the argument of our trigonometric function. I get theta minus 53 degrees is equal to 0. So cos inverse of 1 is just simply 0. Therefore, in that case, then solving for theta here, theta is 53 degrees. Perfect. Okay. So there we have it then. That gives us the solution to part B. Now for the next part of this question, then part C here, we now have a little bit of context applied to the question here. So the temperature, F of T of a warehouse, is modeled by using this equation here, where T is the time in hours from midday and T is between 0 and 24. So for part C then, all we want to do here is find the minimum temperature of the warehouse as given by this model. Now, what you need to recognize here then is that we can actually connect this equation here to our answer from part A and part B, right? So what I've got here then is 10 plus 3 cos of 15t plus 4 sine of 15t. And just notice here then, this part is very, very similar to what we had in part A, right? The only difference here then is the argument is slightly different, but that doesn't really matter. So what I can do then is rewrite f of t using our answer from part A. So f of t is equal to 10 plus, so what I've got here then is this, which is just the same as this, but with a slightly different argument. But again, that doesn't matter. I've got 10 plus 5 cos. So 5 cos of, replacing theta then with 15t, I get 15t minus 53 there. Okay, or minus 53 degrees. Now, if I want the minimum temperature here then, that would be when cosine is minus 1. So 5 times minus 1 is minus 5. So therefore, the minimum temperature then, so the minimum temperature here is, it's going to be 10 minus 5, which gives us 5 degrees there. So the minimum temperature is 5 degrees, and the minimum occurs then, so the min occurs here when, so that is when cosine here of 15t minus 53 degrees is equal to minus 1. So cosine of 15t minus 53 degrees is equal to minus 1 there. Okay. And that is absolutely fine there for part C. Doesn't want anything else other than that. In fact, for part C, didn't even want the minimum, or when the minimum occurred here. I've just kind of done that all in one line, but or all in one part, but that's absolutely fine. So for part D then, I've already done part of the work in here. But all I want to do then is find the value of T when this minimum temperature occurs. So I know then that the minimum occurs here when cos of 15t minus 53 degrees is equal to minus 1. So we'll apply that here then for part D. So what I need to do here then is solve this equation here for T. So cos of 15t minus 53 degrees is equal to minus 1. So all I'm going to do here is take cos inverse of both sides, right? I want to solve for t. So on the left-hand side, I get left with the argument here of our trigonometric function. So I get 15t minus 53 degrees is equal to cos inverse of minus 1. So cos inverse of minus 1 is 180. So I've got 15t minus 53 degrees is equal to 180. So add 53 to both sides. So 15t is equal to, so what is that, 233? So 233, let me just quickly grab my calculator as well. So obviously I can't do 233 divided by 15 off the top of my head. I'm not quite that good at mental maths. But just put it into your calculator, right? So t is equal to 233 divided by 15. And therefore what I get here then for t, to one decimal place here is 15.5 there. Okay, and that is to one decimal place here. And there we have it then. So that gives the solution here to part D, and the solution then to, what question are we up to? Question 6, right? So perfect. So moving on to the next question here, question 7. As we can see then, we've got 3 different parts to this question. Part A, nice and straightforward, just a partial fraction decomposition. Part B again, pretty straightforward, just some simple integration. And then part C is a quick follow-on. Well, I say quick, maybe not so quick, but as a follow-on then, all we want to do here is find the particular solution of this differential equation here. So let's just go step by step here. So for part A then, all we want to do here then is take this algebraic fraction here and split that up into partial fractions. So what we get here then is 5 all over x minus 1 times 3x plus 2. Okay. Now, if we're going to take this algebraic fraction here and split that into partial fractions, then what we'd obtain here is a over x minus 1 plus b all over 3x plus 2. Like so. Okay. Now for the right-hand side here then, let's just get this over a common denominator. So I'd get a times 3x plus 2 plus b times x minus 1 is equal to the numerator of the left-hand side, right? Which in this case is simply 5. And at this point here, all I now want to do then is choose values of x to eliminate both a and b here. So for example then, if I let x be equal to 1, well, I get b times 1 minus 1, which is 0. So b times 0 is just 0, and we've eliminated b there. And in that case, then we can go on to solve for a, right? So if x equals 1, like we just said, this term here is just 0. I get 3 times 1, which is 3, plus 2 is 5. So 5a is equal to 5. And then finally, right, just divide both sides by 5. And in that case then, oops, a is equal to 1. Nice and easy, right? And then doing the same here for b. So for example then, if I let x be equal to, minus 2 over 3, then what do we get here? So 3 lots of minus 2 over 3 is minus 2, plus 2 is 0. So a here is multiplied by 0. That just disappears. And then we can go on to solve for b here. So minus 2 over 3 minus 1, that is minus 5 over 3. I get minus 5 over 3b is equal to 5. Okay? So dividing both sides here by minus 5 over 3 then, in that case, what we obtain here for b is that b is equal to minus 3 there. Okay? So if we express then this fraction here, this algebraic fraction in partial fractions, then what I'd obtain here is 5 all over x minus 1 times 3x plus 2 is identical to, so it's a over x minus 1, where a is 1. So 1 all over x minus 1 plus b, where b then is minus 3. So I get minus 3 all over 3x plus 2 there. Bosh, good stuff, right? Should hopefully be nice and straightforward there. I can't really see any other issues in terms of difficulty there, right? So yeah, so that gives the solution to part A. Now for part B then, let's just do that over here. We want to find this integral here. Now just notice then, this integral here, or my integrand, is the same algebraic fraction that we had in part A. So rather than trying to integrate this algebraic fraction here, it's much easier to integrate the partial fraction decomposition, right? So rather than integrating this here, we're going to integrate the following. So we have the integral then of, so I've got 1 over x minus 1, like so, minus 3 all over 3x plus 2. Like so. I'm integrating here then with respect to x. Okay? Now you should recognize then that the derivative here of my denominators then is the same as our numerators here. So what that means then is my integral here, well, if you find it easier, by the way, you can split this up into 2 separate integrals. I do think that's unnecessary, but if you do find that easier, that's absolutely fine. But in that case, then what I'm going to get here is ln of my denominator here. So ln of x minus 1. So ln of x minus 1 minus them. So minus ln, again, the derivative of 3x plus 2 here with respect to x is simply 3, which is my numerator. So no adjustment here is necessary. So I get minus ln of my denominator here of 3x plus 2. Good stuff. And just be very, very careful here, right? We have no limits on our integral, right? So don't forget then our constant of integration plus c there. Good stuff, right? That gives us the solution to part B. And then finally here, we have part C. So for part C then, all we want to do here is find the particular solution of this differential equation here, for which y is equal to 8 at x equals 2. We need to give our answer then in this form here. So y is equal to f of x. Right, so let's have a look then. So for part C here, what I can see straight away, right, is I've got x minus 1 and 3x plus 2. And I've got these here then as our denominator. So I would expect at some point here, we can use our answer from part A and part B to help us answer part C. Okay. Now what I'm going to do then is split, well, not split, but separate the variables here, right? If I want to solve this differential equation, I need to separate the variables. So on the left-hand side here, what I want then is anything in terms of y, and on the right-hand side here, anything in terms of x. So on the right-hand side here, like we just said then, it's going to be anything in terms of x. So that's going to be 5. So in fact, let me do the left-hand side here, right? Why am I starting with the right-hand side? I'll start with the left-hand side. So I'm going to divide both sides here by y. So I get the integral then of 1 over y dy. Okay, so don't forget then anything here on the left-hand side is in terms of y. And if I want to solve this differential equation here, we also integrate both sides. So I'm kind of doing that preemptively, but that's something that you should be doing anyway. It's a good habit to get into. And that is equal to, so now on the right-hand side here, we get the integral then of, so on the right-hand side here, we just simply get this, right? Because I've divided both sides by y. So on the right-hand side here, I've got 5. I now need to divide both sides by x minus 1 and 3x plus 2. So I get 5. So 5 all over x minus 1 times 3x plus 2. Perfect. Okay. And don't forget here that we're integrating with respect to x. So the left-hand side here, this integral, nice and straightforward, right? That is simply ln y here. To get ln y is equal to, now this integral here, we've just evaluated that, right? As part of part B. So this integral here is ln of x minus 1 minus ln of 3x plus 2 plus c. Okay. So what I can do here then is express this difference of logs here. They are natural logs, but that doesn't matter. Express this difference here of logs as a single logarithm. Okay. So I've got ln y is equal to ln of, so we get x minus 1 all over 3x plus 2 plus c. Okay. And at this point here, what I'm going to do then, I kind of meant to go a little bit further up, but it doesn't matter too much. I'm going to use then these boundary conditions here. So use y equals a at x equals 2. Okay. And by doing this then, we can now solve for c here. So ln y is, that's ln 8 is equal to ln of, so I get 2 minus 1, that's 1, over 3 times 2, so that's 6, plus another 2 there, gives me 8. Okay, we'll get the plus c here. So, just solving for c here, right? So that is ln 8 minus ln of 1 over 8 is equal to c. So let's just write c here as a single logarithm. So c is equal to ln 8. So ln 8 all over 1 over 8, which is just the same then as ln 64. Okay. So I want here my answer in the form y equals f of x. So what I've got here then is, I should be slightly careful here. So ln y is equal to ln of x minus 1 all over 3x plus 2 plus ln 64. Okay. And like we said then, we just want y here. So I just need to take the exponential function here of both sides, right? So I'm going to get e to the ln y on the left-hand side, which is just simply y, is equal to e to the ln then of x minus 1 over 3x plus 2. I've also got this here. So I've got e to the ln of x minus 1 over 3x plus 2, and then e to the ln 64. So I've got x minus 1 over 3x plus 2 here because e to the ln, they just cancel. Just get left with x minus 1 over 3x plus 2 times by it again. So e and ln just cancel. I get 64 lots of this here. So therefore y is equal to 64 times x minus 1 all over 3x plus 2. I feel like I went about that in a slightly messy way. I probably could have done that a little bit neater, but there we go. That is your solution. Okay. So there we have it then. That gives the solution here to question 7. So for the next question here, question 8, we have a question on differentiation from first principles. So what I've got here then is theta, and theta is measured in radians. And we want to prove then from first principles that the derivative of sine theta is cos theta. We can also assume the following here. Now, differentiating sine theta and cos theta from first principles is something that you should be able to pretty much do in your sleep, right? For 5 marks, all things considered, this is pretty generous. So where do we begin here then? Well, let's just start then by stating the result here for differentiation from first principles. So f prime of x here is equal to the limit as h tends to 0 of f of x plus h minus f of x all over h. Okay, this result here then is all we're going to simply use to prove from first principles that the derivative of sine theta is cos theta, right? Well, alongside this here and these limits here as well. So let's get started then. So the first thing that I always do here for differentiation from first principles is start by listing f of x and f of x plus h here. Now, obviously, rather than x, we have theta, but it doesn't really matter. So f of theta then. So f of theta here. In fact, let me just do that over to the left-hand side here, just so I've got a bit extra in terms of room here. So f of theta then. So f of theta here is what we're starting with, which in this case is sine theta. So we have sine theta there. And then for f of theta plus h, well, in that case here, then we simply get sine of theta plus h, right? Hopefully nice and obvious there. And at this point here, we now have everything that we need then to find or prove from first principles this derivative here. So what do we get then? So f prime of theta here is equal to, so it's the limit as h tends to 0 of, so I've got f of theta plus h here. So that's sine of theta plus h. So sine of theta plus h here, minus then f of x, so minus f of theta here. So minus sine theta all over h. Okay? So at this point here, the only thing that we can really do then is use this result here, right? Sine of a plus or minus b. So we've got sine of theta plus h. So refer to your formula book then if you don't know this off the top of your head or by heart. But what I get here then is the limit. And you do need to write this at every step here, really. It gets a little bit tedious and repetitive. I really do appreciate that, but it is important here. So the limit as h tends to 0 of, so sine of theta plus h here. So what I get then is sine theta cos h. So sine theta cos h plus cos theta sine h. So plus cos theta sine h. Okay? And don't forget as well, of course, the minus sine theta here. So minus sine theta, and all of this here then is over h. Okay? Now, at this point here, I want to start working towards these results here, or these limits, right? So what I'm going to do here then is group this sine theta cos h and the minus sine theta together. So we get the limit as h tends to 0, as h tends to 0 of, like we just said then, sine theta cos h minus sine theta. So grouping those together. And I've also got cos theta sine h as well. So plus cos theta sine h. And again, all of this here is over h. Okay? Now, the next step here is probably the trickiest for, or starting to get towards probably the trickiest part of this question here for many students. So what I'm going to do then is split this limit up here into two separate limits, right? We call this linearity. So what I'm going to get here then is the limit as h tends to 0 of, so I've got the first part here, so sine theta cos h minus sine theta all over h. So sine theta cos h minus sine theta all over h, plus then, again, I've got another limit here. So the limit as h tends to 0 of cos theta sine h all over h. Okay? So again, what I want to work towards here is these two results. So sine h over h and cos h minus 1 over h. So for the inside here then of this limit, right, what I can do then is factor out sine theta here. Okay. So when I factor out the sine theta here, I've got sine theta times cos h minus 1 over h, which is this result here. This part here, well, if you think about the cos theta sine h over h, we were to essentially write this as cos theta times sine h over h. We've got this result here. So we're starting to cook here, right? Things are looking good. So what I'm also going to do here, again, using linearity, is we can take the sine theta outside the limit here, and we can also do the same with cos theta. So again, this is where things get a little bit trickier, and probably the trickiest part of this question here is just being able to spot this, right? And understanding that we can use these properties of limits here. So we take the sine theta outside this limit here. So sine theta times, so let me get rid of this here, right? That doesn't look particularly pretty. So I've got sine theta times the limit. I'm getting carried away here. So sine theta times the limit as h tends to 0 of, what I've got left with here then is cos h minus 1. So cos h minus 1 all over h. Perfect, right? This here is exactly what we want. Perfect. Looks good. Again, using linearity here, then we can take the cos theta outside the limit. So I get cos theta times the limit as h tends to 0 then of, what I get here then is sine h over h. Perfect. So sine h over h. Again, perfect, right? That is exactly what we want here. And using these limits here then, so as h tends to 0, I've got sine h. So sine h over h tends to 1, and cos h minus 1 over h tends to 0. So in that case then, so therefore, f prime of theta here is equal to, so I've got sine theta times by this limit here. Now, as h tends to 0, cos h minus 1 over h tends to 0. So I've got sine theta. So sine theta times 0 plus, we've then got cos theta times by this limit here, but as h tends to 0, sine h over h tends to 1. I've got cos theta. So cos theta times by 1. Well, clearly, sine theta times 0 is just 0. Cos theta times 1 is simply cos theta. Perfect, right? We get cos theta there. And therefore, then, the derivative here, so d by d theta of sine theta here is equal to cos theta as required. Bosh. Good stuff. And there we have it then. So hopefully, wasn't too challenging. But again, like I said, this is something that you need to be able to do here in your sleep, right? Being able to differentiate sine theta and cos theta here from first principles. So that was sine theta from first principles. If you also want to see cos theta from first principles, please do go and check out our predicted paper 2, where we cover that as part of that paper. Okay, so there we have it then. That gives us the solution here to this question. So moving on to the next question here, then question 9, where we have a question on sequences and series. So for the first part of this question, then all we want to do here is find the value of the following series. So for part 1 then, what you need to recognize here, and again, this is something that you should be looking out for anytime you have a question here dealing with series. If we're going from r equals 1 to infinity, then what I've got here is a geometric series, and we're looking to just find the sum to infinity of that geometric series, right? So what I need here then is a and r. So what is a and r here? So a is my first term here. So that is when r equals 1. So I get 6 times 1 over 4, so 6 over 4, which is 3 over 2, which is 1.5. So a is 1.5. And then for r here, the common ratio, well, when r equals 1, I get 6 times 1 over 4. When r equals 2, I get 6 times 1 over 4 squared. When r equals 3, I get 6 times 1 over 4 cubed. So r in this case here is just simply 1 over 4, right? Or 0.25, whichever you prefer. I'll keep it as a decimal, but it doesn't really matter. So 0.25 there. So, like we said then, we're looking for the sum to infinity here of a geometric series. So in that case then, the sum to infinity here is equal to a all over 1 minus r. So a here is 1.5 all over 1 minus r here, where r is 0.25. Just put this here then into your calculator, and if you do this correctly then, what you should find here for the sum to infinity is 2. So this series here then, or the value of this series here, is simply 2. So that gives the solution here to part 1. So for the next part of this question here. So part 2 then, we've got part A, part B, and part C. So for part A then, what do we want to do here? Well, to begin with, we have a sequence U1, U2, U3 that is defined by the following recurrence relation. So for part A then, what we want to do here is show that this sequence is periodic. So for part A then, let's just start here by listing U1, U2, U3, U4, so on and so on. And at some point here, if this sequence is periodic, then it should start to repeat. So U1 here, well, we're already given that, right? That's 3. Now for U2 then, what do I get here? So I've got 3 minus 3, which is 0. So it doesn't matter what the denominator here is, it's just 0. For U3 then, what I get here is, so I get 0 minus 3, so minus 3 over 0 minus 2, so minus 3 over minus 2, which is 3 over 2. So what do we get here then for U4? So for U4 then, it's going to be 3 over 2 minus 3 all over 3 over 2 minus 2. So just put that into your calculator, right? We don't need to do that by hand. What we should find then for U4 here is we get 3. And because U4 is equal to 3 here, what I can see then is that U5 would be U2 here. So in other words, U1 is equal to U4, like so. And therefore then the sequence is periodic. So therefore, the sequence is periodic. And there we have it then. So that's all we need there for part A. Now for part B then, it just says state the order of this sequence. So in this case here, my order is 3, right? Because I've got 1, 2, 3. And then after that, we arrive back at U1. So 1, 2, 3 there. It's order 3. So order 3. And now for part C then, it says hence find the following summation here. So what I've got here is the summation of UN from n equals 1 to 70. So how do I do this here? Well, what I've got then is a periodic sequence. So this just keeps repeating here every 3 terms of this sequence, right? So I've got U1 plus U2 plus U3. That is equal to some value, but then U4 plus U5 plus U6 is the same value. Same again, we just keep going, right? So how many times then can I group those 3 terms together? So for example, U1, U2, U3, so on and so on, up to U70. Now, like I just said then, U1 plus U2 plus U3, this here would have the same value as U4 plus U5 plus U6. Same is true for U7 plus U8 plus U9, plus so on and so on. So how many times then can we group those together? Well, we just take 70 here, the upper limit to sigma, and we just divide that by 3. And I get 23.3333, so on and so on, right? So I get 23 and a remainder here. So what I've got here then is 23 lots of U1 plus U2 plus U3, so on and so on. And then I just get left with this final term here of U70. I get 23 lots of, so U1 is 3, U2 is 0, U3 is 3 over 2. Let me just get left with U70 here, which would just be 3, right? Just keeps repeating. Just get plus 3 there. So just put this here into your calculator. If you do this correctly then, we should find here is we get 106.5 there. Okay. And there we have it then. So that gives the solution here to part C and the solution to question 9. And there we have it then. So we covered 9 questions in total together here for this video. I know I did mention at the beginning of the video 10 questions, but who's really counting? So before I conclude the video here, And I'd also just want to quickly mention as well, you might have already seen them, but just in case you haven't here as well, we do also have predicted papers for 2025. So just in case you've not seen these already, we've got Set C Paper 1. So this is our predicted paper 1 for 2025, and also Set C Paper 2. So our paper 2 here for the 2025 predicted paper series. If you haven't had a go, please do have a go at these two papers here. You can find our video walkthrough on YouTube, right, at AJMaths. So Set C Paper 1 and Set C Paper 2. We also have Set A and Set B as well. They're also available on our website, ajmaths.co.uk. So if you're looking for even more A-level maths revision, be sure to check out our website, ajmaths.co.uk. And then finally, for the very last point here, the question that you've worked through for this video here, I'm also going to put those together in a paper. So the marks and kind of like the timing or the difficulty isn't going to be perfect, right? I'm just putting together a compilation of questions here based on the list that I introduced at the beginning of this video here. But again, if you want to have a go at that, that will also be available on our website, ajmaths.co.uk. And at this point here, I don't really have anything else to add, right? So all I want to say then is best of luck with paper 2 next week. Fingers crossed, it's a really good paper. I do think it might be a little bit more challenging than paper 1, but that doesn't mean it can't still be a good paper. So best of luck with paper 2. Please do check out our website, ajmaths.co.uk, if you are looking for even more A-level maths revision. So that brings us to the end of this video here. As always, thanks for watching.